All right. Good afternoon. My name is Devendra Das Sarma. We'll talk about Compute Express Link. It's a standard for effectively heterogeneous memory and computing systems, heterogeneous compute, open industry standard. We'll take a look into CXL and its evolution. Agenda-wise, we'll talk about the industry landscape and where CXL fits in. CXL has undergone 3 generations of specification development. So we'll talk about the first generation, CXL 1.0, CXL 1.1, which basically was around enabling heterogeneous compute and memory expansion. We'll then talk about CXL 2.0, which was pooling of memory resources, switching, and some security enhancements. And then we'll talk about CXL 3.0, which doubled the bandwidth and did a lot of other interesting things like peer-to-peer, fabric topologies, composable compute, and then we'll conclude with your questions. So, in the industry landscape, what we see is that, of course, proliferation of the cloud computing, deployment of AI and analytics, and we are seeing the cloudification of network and edge, and that's basically giving there's a lot of demand for compute, there is a lot of demand for memory, there is a lot of demand for all these sets of things, right? Storage. We are in the midst of this virtuous cycle of innovation. So, more data needs to be processed, means your infrastructure needs to be more capable, which means you're able to do more. So it keeps continuing. So this is going back to around 2019, right? So that's when we started CXL, which was a new breakthrough for a high-speed fabric. And what it did was it enabled a high-speed, efficient interconnect between CPU, memory, accelerators. Effectively, it's the central interconnect between different components in the system. And we built on the PCI Express infrastructure, leveraging PCIe physical layer, electrical interface, even protocols. What we did was that we added memory semantics and cache coherency semantics on top of the PCI Express model. And the goal was to enable fine-grained resource sharing for higher performance in the heterogeneous compute environment. So without having to move data back and forth, how can we do a finer grained data sharing, and then of course memory disaggregation and memory pooling and all of that to get around the memory wall problem. And CXL is delivered as an open standard. This is a little dated slide. CXL 3.0 specification was available in August of last year. And future generations of CXL will be built on that and continuously innovate as we talk about, we'll see. 250 plus member companies. We started in March of 2019 with 9 promoter companies. And this is the current group of board members. They're listed here. You can look at them. Pretty much the who's who in the field of all CPU vendors, all memory vendors, all cloud, enterprise, storage, networking, you name it, all of them are there. So this is the CXL specification timeline. March 2019, we started the consortium, as I said, with 9 promoter companies. CXL 1.2 specification was released at that time. Intel donated the first CXL specification. The consortium was incorporated somewhere around, June, July timeframe. I don't quite remember exactly when, but sometime in 2019, Q2, Q3 timeframe. September 2019, it's here. It was incorporated, and at the same time, the consortium released the 1.1 specification. And what it was is basically clarifications on the 1.2 specification, and most importantly, how do we do compliance? So 1.0 was pretty much intact. We added compliance, and there were a bunch of things that people had questions. So clarifications, all of that. And we'll see what each and every generation of the specification did. And that's why you'll see me saying CXL 1.2/1.1 because, other than compliance and clarifications, they're pretty much the same. CXL 2.0 we released in November of 2020. And we'll talk about what was there. And then August of 2022, CXL 3.0 was released. And stay tuned for new things coming up. So what's the approach of CXL, right? Let me see if I have, okay, to verbalize it. Normally I have a slightly different slide to talk about the motivation here. But basically, with PCI, so CXL is built on PCI Express infrastructure. That's the first point, right? And as I said, we added memory semantics on top of that, and we added some caching semantics on top of that. So 3 protocols. CXL.io is fundamentally PCI Express, CXL.mem is memory semantics, and CXL.cache, which is caching semantics, which is basically in the picture you will see CXL.io, CXL.cache, and CXL.memory or CXL.mem for short. Because caching and memory semantics got included, so there are 3 pillars, right? One of them is, of course, coherency, and I'll talk a little bit about the motivation behind that. Maybe we can talk about it in the next slide when we get there. It will make better sense. CXL.cache and the CXL.mem, because of coherency semantics, because of coherent memory semantics with CXL.mem, these are very latency sensitive. So what kind of latencies are we targeting? We are targeting realistically, there is a number here, less than 200 nanosecond load to use, and load to use means that your CPU had a cache miss, your instruction had a cache miss, how much time did it take for that particular core to get the data, going across the link, coming back, going through the entire infrastructure. Normally, if it is a cache miss on the local socket, that latency number is around less than 100 nanoseconds. And if you go off to another CPU socket today in the NUMA system, it's less than 200. Note that I'm not giving exact numbers. I'll give you some exact numbers, but these numbers are rounded up, so to speak. Numbers to change generation to generation. So the idea here is that if memory expansion looks like it's memory attached to a nearby socket, we know how to deal with that. In a symmetric multiprocessing cache coherent systems, we have dealt with it for decades. So that's an easy thing. So that's the reason why that's a low latency. And last but not the least, it's asymmetric complexity. And by that, what we mean is orchestrating cache coherency tends to be very involved with the underlying microarchitecture. How you orchestrate cache coherency depends, varies quite drastically even within the same company, and have been in 2 companies, HP and then now Intel, right? Both do SMP systems, as we all know, server systems. Orchestrating cache coherency changes from generations of CPU to generations of CPU, and definitely by the time you are in different ISAs, even within the same ISA, from company to company, it changes. So architecting how that orchestration works, it's not going to be something stationary. It's going to keep changing. However, what we know is that cache coherency is, on a simplified level, from a caching semantics point of view, basically, messy, modified, exclusive, shared, invalid, right? This is standard protocol, everybody knows, right? So, for example, you say that, hey, I need to read this cache line in a shared fashion, or I need to read this cache line exclusive. And then if there is a write, I do a write back. These are all pretty standard stuff. These do not really change, right? It's the orchestration. How do you deal with conflicts? All of these things, right? Where do you store that directory, right? Is it a snoop filter? All of these things, they change, okay? The fundamental mechanism, underlying mechanism, it's a simple set of actually about a dozen instructions, okay? And then, occasionally you have to send a snoop saying, hey, you need to give up that cache line. You have cached it, you need to give up because somebody else wants it, right? So what happens with these, what asymmetric complexity means is that in this picture, if you see, there is a home agent, and that home agent is the one that is orchestrating. Every CPU today, modern day CPU, has a home agent that basically encapsulates how this orchestration works. And as I said, it changes from generation to generation, architecture to architecture. So, and people have it. So we said, okay, Whichever way you do it, great. What we are going to do is just give some simple instructions so that on the other side, in this case, an accelerator can cast the lines, right? I mean, this is where it asks for something shared, private, sorry, I keep saying private, exclusive, some terminologies stay from your start of your career, I suppose. And you can ask for a snapshot, whatever. And then, if there is a snoop, you can do, give a snoop response, you can do invalidate. So it's some of those things, right? So devices don't really need to worry about home agent. They can just piggyback on whatever home agent exists in the host processor. And by the same token, if you are a memory expansion device, you don't really need to worry about how do I orchestrate cache coherence. Even though the memory is mapped to the coherent memory space, at the end of the day, it's memory. What business do you really have in orchestrating cache coherency? Well, you don't, if you choose not to. So, your memory flows are, again, simple things like, hey, I want to read this location, I want to write to this location. And yes, there will be some metadata bits, for example, things like directories. So there are a couple of bits that we have defined. As long as you can store those bits and as long as you can send those bits back, we are good to go. Right. So that's why it is asymmetric, so that the complexity is held low. And it's not like, we are adding more complexity to the host processor. As I said, the host processor has a home agent to begin with. Okay. So these are the three pillars for CXL when we started. Of course, when we started, it was a direct attach model. And here are the usage models, and I will talk through some of the rationale here. So PCI Express is also a load store interconnect. In other words, things are memory reads and memory writes. So the question is, okay, why are we adding coherency and memory semantics to it? And the reason is PCI Express is fundamentally non-coherent across the link. Yes, it is ordered I/O, but it is non-coherent. There is a producer-consumer ordering model that gets enforced on the CPU side, which basically merges the cache coherency semantics with the load store semantics. It does all the magic underneath, so that devices effectively work as non-coherent extensions. And that really works well because you don't want the hundreds of device manufacturers that are out there to really worry about every other CPU's cache coherency mechanism, which changes, quite frankly, right? Year over year over year. Now, the question is, okay, why add coherency to this mix? And, a lot of these heterogeneous processors, first of all, they want to participate in finer grain coherent access mechanism. Otherwise, what will happen is anytime you are asking an accelerator to process something, you have to effectively transfer your entire data structures and the command and saying, okay, now do this job, and once you're done, send it back to me, right? So you're transferring entire data structures back and forth. That works for quite a few applications, but especially if you're doing very finer grain kind of processing, this is where coherency helps. So I'll go through the first couple of examples, then we'll talk about the memory wall so there are actually 4 problem statements that CXL has solved so far. This is the first one, heterogeneous computing. So type 1, there are 3 types of devices with CXL 1.0 or 1.1, type 1, type 2, type 3. We're not very creative with names, so that's our nomenclature. Very simple and straightforward, okay? So what type 1 does means is that the device has the .io, which is the PCI Express protocol, the non-coherent load store, and you add CXL.cache. What are some of the usages? Well, things like smart NICs are a good example. So if you're doing, for example, partition global address space, the ordering model there is different than PCI Express ordering model, memory ordering model. So for example, if you send something on the PCI Express links, your writes, subsequent writes can bypass a prior read, and that may not work well. So what happens is that if you are trying to implement that in the NIC, you're going to now serialize it, get the read completion, then only you're going to do the write. So that's going to serialize things, right, whenever you need that ordering. Well, what do we know about cache coherency? Well, I can issue prefetches in any order as long as I'm completing those instructions in the device in the program order that is desired, because what cache coherency does is the moment you write in your local cache, it's committed to the memory. Whether it is physically there in memory or not, that's the beauty of cache coherency. It takes care of that. So that's one type of usage models there. The other has to do with like atomics. A lot of these advanced NICs have very advanced form of atomics like double precision floating point and all those kind of things. Yes, you can add them in a PCI Express semantics. The thing is that, by the time you add something into the specification, by the time it goes through it, by the time it gets reflected in the volume CPUs, you're looking at a good 4 or 5 year lag by the time products come out, and you probably have moved on to doing something even more interesting, right? Well, if you can cache the location in your memory, you can complete them, you can do whatever atomics you want. It's coherent, right? It's coherent memory. So those are some of the usages, right? I mean, that's the heterogeneous processing, which is the first problem statement. And accelerators with memory examples are, again, your GPU, dense computation. These have all three types. So not only do they use, of course, .io, the caching semantics, but also they have memory and they want to map that memory into the system address space, so that if that part of that data structure that is predominantly being accessed by the device belongs to the device side, although it is mapped to the coherent address space, and vice versa. You're trying to just minimize the amount of data transfer across the link. Second problem statement, we are all up against the memory wall. And what do we mean by that is there are few things that are going on. First is, if you look at the amount of memory bandwidth that is available per core, it's going down over time. As cores are being capable of, and this is not just, x86 cores, this can be any GPU core and all that. Everybody has the same problem statement. So what's happening is that these things are becoming more and more capable. And of course, with chiplets and all of that, we are able to pull in more number of cores. We are able to cool the package more, right? And what's happening on the memory side is that the memory bandwidth, it's going up, but it's going up at a crawling pace, right? So that's the reason why, you will see that, when I started and when a lot of us probably started, we had one DIMM, one DIMM channel, right, for every CPU socket. Then it went to 2, then it went to 4, then it went to 8, then 12, then 16, right? And these are like 300 pins. These are not lightweight. These are like pretty heavy duty stuff, and all of those are getting on the board. And these DIMMs are sitting on very constrained, thermal envelope side, right? Because you got the CPUs that are running hot. You got the DIMMs next to that, right? And they have to be nearby because they are essentially multi-drop buses, right? Effectively, all the other interfaces, whether it is I/O, PCIe, for example, moved from bus to link way back in 2003. CPUs moved from front-side bus to link-based architecture sometime around 2005-06 in the volume segment. Memory continues to be on the multi-drop bus kind of a thing, and there's a good reason behind that, and that's because the latency is really, really low, right? And of course, memory devices want to be bidirectional and all of that. Those are all good stuff. The problem is, that's first problem, is that the bandwidth is going down over time. It's not even keeping up. Forget going up, it's going down over time per core, right? In spite of adding more memory bandwidth per socket, because the trend is down. Second problem statement on that memory wall is cost of the memory. It's flat. As you are doing more and more processing, you need to feed the beast from a bandwidth point of view, but also you need to feed the beast with a capacity point of view. And memory capacity, especially with the higher performing one from a gigabit per dollar kind of point of view, that has been flat, which means that memory is a larger share of wallet in the server system. So that's problem number 2. So where does CXL help? Well, first of all, CXL will have more latency. Let's get that right off the bat, right? As I said, the latency is equivalent to a NUMA hop away latency. But what do I get with that? If you look into, so that's where the memory bandwidth expansion comes, the memory capacity expansion comes, right? Both from a bandwidth and capacity point of view, and also the storage class memory. In other words, you can have the not so expensive memory and have like a memory tiering support built into CXL just to get around the second problem statement, which is the memory wall problem. So just to give you a comparison, right? Right now, PCI Express Gen 5 32 gig is widely available. So if you do 32 gig and you consider a by 16, a 16 lane link, which is the CXL one, is 128 gigabytes per second net, right? I mean raw bandwidth. And how much do we get? So 64 pins, 128 gigabytes per second raw on a DRAM channel with, pick your favorite, right? DDR, whatever, 6400, DDR5 6400 or whatever, right? How much bandwidth do you get? You get around 50 gigabytes per second or 300 pins. So clearly, per pin bandwidth, there is no way to even get close to what PCI Express offers. And by the way, that number, that 32 gig number on PCIe is already at 64 and looking to 128 very soon, right? It doubles. There is no way you can keep up with an exponential thing where the latency has been flat pretty much. So that's where, again, latency wise, you are going to lose, but cost, all of these things, you're going to come out ahead, right? Bandwidth per pin. So that was CXL 1.2, the first two problem statement, heterogeneous computing and getting around the memory wall. Third problem statement has to do with stranded resources in the data center. And by that, what we mean is, today, without CXL 2.0 deployment, if you look into what we have, you basically have a server where you got your own memory for every server, you got its own GPUs or FPGAs or what have you, right? Accelerators. Those are all tightly coupled systems and they belong to that server. But what I mean by belonging to that server is, for example, if I have a server, let's say that has a terabyte of memory, DRAM memory. I got another server, I got, let's say 10 servers in a rack, right? Each of them has a terabyte of memory. And one of the server has a temporary need for, let's say, 1.5 terabytes of memory. And the rest of the servers are only using half a terabytes of memory, right? Well, you really cannot go and ask your neighbor saying, hey, can I borrow that memory of yours? Well, no, you can, except it becomes an RDMA or something. You have to go through the networking stack. It really doesn't map into your coherent memory space. So effectively, what's going to happen is that you're going to go and page in and out and suffer the performance consequences. So same way with accelerator and all of that. So people, they tend to over provision resources, saying that I think I might need 90% of the cases I will need this much, so I'm going to over provision everything. And basically that's stranded resources, which is not good from a total cost of ownership point of view. It's not good from, a power point of view either, right? And of course, performance, when you need it, if it is not there, what happens, right? You just take the hit. So that's the third problem statement that we solve with CXL 2.0. And even though I'm calling it memory pooling, you can use the same notion for accelerator pooling here. And the basic idea is this. The top row, which is the H1, H2, all of those are independent servers. So they have their own memory, right? In our example, let's say, you decide to put, let's say 1 terabyte memory in each and every one of them. You think 1 is the optimal number. So let's stick with 1 terabyte there. In the bottom, you maybe put a few terabytes of memory, and that memory is available in a pool. And that pool can be allocated to somebody whenever there is a need, and they can be deallocated whenever the need goes away. So for example, H1 needed 2 terabytes of memory. It has 1 terabyte. So you can always go to the pool and ask for that terabyte. Once that job is done, you release that terabyte back to the pool. So same way with accelerators, you can have some nearby and some on the other side. And by the way, even though we saw a switch here, you can have devices that are multi-headed and connect directly, and that's how you can do pooling. So, and this notion of pooling doesn't have to be on all the memory in a given device. You can even, CXL 2.0 allowed for up to 16 servers can have different parts of that memory associated with that devices. So those are known as multi-logical devices, MLD for short. So that's the second problem statement that CXL 2.0 solved, which is, the third problem, right? The first two were solved in with CXL 1. The third one is around stranded resources, so memory pooling and accelerator pooling. Another thing is, of course, switching capability. Of course, it allows for greater fan out. These are standard things. CXL 1.0 was fundamentally a direct connect. With 2.0, we allowed for switching. So, and there were a few other things that we did. So we talked about resource pooling and resource disaggregation. And, the way you add or remove resources is through onlining or offlining, which basically is similar to a hot plug flows. We know how to do that, right? For type 1, type 2 devices, these are completely assigned to one. And as I said, for type 3, which is the memory, we can do pooling at a granular level. Up to 16 servers at a time can pool the memory. Still very low latency access. And we also define persistence flows for the persistent memory. So these are architected in CXL 2.0 specification, as opposed to, waiting for some amount of time to make sure say, hey, roughly if I wait for a minute, everything would have been, I flushed everything, it should be in the persistent domain. No, there is a proper architecture flow with CXL 2.0 and there's a proper handshake. We also defined a fabric manager along with APIs, because once you're dealing with multiple servers that are pooling resources, you need to define which entity is the one that is orchestrating these accesses across them. For security, we added things like authentication, encryption, all of those got added. And the fundamental contribution, as I said, right, was that third problem statement is that what CXL did was that this is the first time a load store interconnect, tightly coupled load store interconnect, goes from a node level to beyond a node level, effectively to a rack or a sub-rack level. And so that was CXL 2.0. Now moving on to CXL 3.0. So, but the trends are the same, right? Which is, you can read it there, but, of course, higher performance, more bandwidth. If you can get for the same latency, same cost, same power, right? Why not, right? Double the bandwidth. We all like to do that. And we talked about how CPU efficiency has been declining, and so effectively keep that problem statement. But in addition to that, we'll go through some of these. There is a peer-to-peer resource sharing challenge, which is the fourth challenge that we solved with CXL 3.0. And we talked about the memory bottlenecks. And so at a high level, what CXL 3.0 did is to solve that with fabric capabilities. We'll go through that. Enhanced memory pooling. We double the bandwidth, which means we double the frequency basically, with zero latency adder, and of course full backward compatibility with the prior generations. So again, this is just a summary of the same thing. We talked about this. So enhanced coherency, peer-to-peer. We're going to go through each and every one of these. And this is a tabular format of what features are there, and we'll go through them. But you can see that it's a progression, right? For example, data rate goes from 32 to 64 with 3.0, and then effectively what 3.0 brought to the table is multi-level switching, fabric capabilities, direct peer-to-peer access, enhanced coherency, memory sharing, which is different than memory pooling. I will explain that when I get there, and multiple type 1, type 2 devices, and of course, fabric capabilities. Let's start with the doubling the bandwidth with the same latency. So, PCIe 6.05, we are on PCI Express infrastructure. So when our PCIe makes the data rate doubling, why would we not take advantage of that, right? So PCIe 6.0 moved to 64 gig, so CXL moves to 64 gig. Same PAM for encoding, same kind of BER assumptions. And by the way, the fleet layout is there. I gave a talk earlier today in the PCIe 6.0. This is an simplified version of that picture. Same bit layout. There are two types of CXL flits. One of them is standard, looks very similar to the PCIe 6.0. That's the CXL 256 byte standard flit layout. The only thing that happens is that the 2-byte flit header moves to the front, but other than that, everything else remains the same. And then there is a latency optimized flit layout. What it does is, you will notice that there are 6 byte CRC for every 128 bytes. So the basic idea here is that every 128 byte at that odd even subflit, you check the CRC. If the CRC passes, you don't even wait till you do FEC, just accept the data. Because the CRC is a much more stronger thing. If the CRC fails, then you wait to accumulate the entire 256 byte. You do the error correction, then do the CRC check. So that way, if most of the time the expectation is you have zero latency add because you're not waiting for anything. You're just 128 byte you're processing. Remember, previously it was 68 bytes at 32 gig. Now it's 128 bytes at 64 gig. So accumulation latency is the same. CRC is pretty much 7-8 levels of logic. So it's practically nothing in hardware. But if there is an error, then you go through the FEC correction, which means you have to wait for the other half to come by if the error happened in the first half. So there is that accumulation latency, and then the FEC correction, which is another nanosecond. So about 2 nanoseconds of extra latency, okay, in the error case. And if you still fail, then of course you go through the link level retry. So there is a paper that goes through all the math behind that. So, but fundamentally, this is what we did, right? So effectively doubling the bandwidth, keeping latency flat. Next comes, and I'll come to the fourth problem statement in a minute. I'm just going to go through the ingredients first and then go to the broader problem statement. Protocol enhancements for device-to-device connectivity. And that's basically, you have these devices. If the memory type is non-coherent, like PCI Express, devices do direct peer-to-peer. They don't have to go through the CPU. But because the memory here can be coherent, then you basically have to go through the CPU in order to resolve coherency. Even though you don't need to cache the location, even if you're doing a non-coherent access to that memory, because it is mapped to the coherent memory space, you always have to go to the CPU and let it resolve cache coherency and then do the write back, right? So you're always going up and then coming down to the other device. So the question is that, do I really need to do that? We're always looking for, hey, what can I do to optimize my performance, right? And what came out of these is two very simple constructs. I touched on the UIO in the other talk in PCI Express, but this was one of the main reasons why we went with UIO. And given that we had to do it here, we said, if we do it in PCI Express, everybody gets it, right? So unordered IO basically says that, okay, there is a producer-consumer model. Remember, I said that I need to access this memory non-coherently. I'm not caching it. So if I do that, the only difference is that it is to coherent memory, which normally happens, right? And today in CPU, with the PCI Express, you go and do IO, it's to coherent memory for the most part, right? So what happens here is that you do the direct access, but then you could be doing accesses to other parts, right? And then the question is, how does producer-consumer work? Because it doesn't work once you go and fork off that thing. Till everything is on a strict tree infrastructure, producer-consumer works. Once you start forking off parallel paths, it doesn't work. You can always come up with the race condition. So what we said is that the enforcement of that producer-consumer ordering moves to the source. So in other words, if device 1 is the one that is generating reads and writes, it needs to make sure that it enforces ordering. In other words, every time it does a write, before it posts a flag, it needs to make sure that the writes got committed. So that is the genesis of the unordered IO. It's not that we went away from the producer-consumer modeling, ordering model. We just said that not every point in the path needs to enforce that. The enforcement just goes back to the source. As a result, the rest of the path can be completely unordered. So that's first thing. Okay, so let's say device 1 sends a write to device 6 to the coherent memory, and it's going to get a completion back, so it knows when it got done. So if it wants to post the flag, it will post the flag. Now I send the write to device 6. Device 6 looks at that data and says that, okay, this is to coherent memory, but my directory says that this line is being held exclusive or shared by another CPU. So what do? I cannot really write to it because then I'm violating the fundamental principle of cache coherency. So we introduced the notion of something called back invalidate. Remember, I said that, you are a memory device. You really don't want to worry about cache coherency, but you only have 2 bits of directory anyway to have to map coherent memory space. That's the metadata. So you look at that metadata, you say, hey, this doesn't look like I can do it. I don't know how to resolve coherency. So all it does is back invalidate is just a memory transaction going back to the CPU saying, you need to help me, tell me when to do this, write or read, because I cannot, I think there might be a potential coherency conflict. So you go do whatever you need to do and tell me whenever it is safe to do so, right? So then the CPU comes back, does whatever thing, and then gives a response to that back invalidate. So two very simple constructs, right? One is unordered IO, the other one is back invalidate. So as a result, now what happens is, not everything needs to flow to the CPU. You can start making distributed decisions, and only in the case of a conflict, coherency conflict, you involve the CPU because it knows how to resolve coherency conflicts. There are some other advantages of doing that back invalidate flow, and this gives an example of a snoop filter where a processor might have, a GPU might have a snoop filter, and if you have a snoop filter, the problem is, that snoop filter cannot be infinitely large as your memory. So, you had to basically back things up in a directory with a proper directory, right, to who has it, those kind of things. And now with back invalidate, you can just say, hey, anytime I got a snoop filter overflow, I just back invalidate some other line and make room for it in my snoop filter. That's what this is trying to show. So it has got some other usages. Some of the other things that we did with CXL 3.0 is, of course, multi-level switches, but most importantly, it's a it's a fabric topology that will come to, and multiple type 1, type 2 devices in addition to just a single one. And I promise I'll come to the fourth challenge here in a minute. So I'm just giving you the ingredients, and I will tell you how they tie together. So we talked about memory pooling. Now there is another concept called memory sharing, and what that means is, pooling is basically saying that, okay, I'm a device, I have, let's say, 256 gigabyte. I give server 1 16 gigabytes, I give server 2 the other 16 gigabytes, and so on and so forth, right? But they don't really overlap. In other words, you cannot use it as a staging area to do a shared data structure. It's just like, this is my sandbox, that's your sandbox. We happen to share the same physical, CXL card, right? Shared coherent memory, on the other hand, says that, of course, you can have the pooling, you have your own sandbox, but there can also be an area where of course, you have different servers, you can have an area where you can use it for your common data structures to pass messages and things of that nature. So then the question is, how do I keep cache coherency? Because if you look at the servers, each of them think that they own the entire coherent space, right? That's the notion, right? If you look into any VMM, BIOS, it thinks it owns the whole thing. Yes, it knows how to deal with somebody else, but that's like an RDMA semantics, right? From a coherency perspective, they think they own the whole memory space. So how do you deal with, how do you deal with multiple processors effectively trying to get into a shared coherent space? You can always do one, but then the problem is, how do you make sure that if one server goes down, it's not bringing down others? Because that's like so what we said is, in this case, you got your, you have your, let's say there is a coherent space. You have to, of course, solve the address mapping thing. That's an easier one. How do they see the same address? They might have different addresses. It might physically be in the same location. But effectively, who is orchestrating cache coherency? Well, remember, we have the back invalidate. In this case, the device really needs to track more than just those 2 bits of metadata. It needs to track which server has it. So it needs extra information. Okay, so these devices are more advanced. Although they're not orchestrating coherency, they know which sets of servers have the data. So if it is shared, and let's say 10 guys have it shared and 11th guy wants it, fine, have it, right? I'm just going to add the 11th one to my list. But anytime there is somebody wants exclusive, then in that case, they just have to send the same back invalidate to each and every one of those 11 ones. And then once they get the response, then they can give the exclusive access to somebody. So now you basically have this mechanism of effectively having shared coherent memory. And it's not going to be very performant in the sense that you can't really deal with a lot of bandwidth, but a lot of the usages are for reads. So those are fine. Reads you can get. if you're doing a many read, many write kind of problem, you can still serve it, but you have to be very careful how many, because coherency scaling tends to be fairly limited. That's the basic nature of coherency, right? So, but it's we allow for all of that. In fact, we define something called global fabric attached memory, which can serve up to 4,095 entities. So, pretty big scalability is built in. So, unordered I/O, back invalidate, all of these things, they enabled us to basically get to all of these multi-level switching and all of that. The shared memory, this is another example just showing how sharing works. So in this case, S1 and S2, both locations are shared. So H1, H2 have it shared, H2, H3 have shared between S2. But with unordered I/O and with this back invalidate, now we are no longer bound by a tree topology. We can have non-tree topologies. We can have parallel paths between source destination pairs. So if we look into what was causing the tree topology, one was the I/O ordering model. So we solved that with unordered I/O. And then the second one, in the case of mostly CXL.cas and CXL.mem, CXL.mem is pretty much unordered. CXL.cas has a little bit of ordering in the sense of snoop and go, global observability, but that's on a per cas line basis. So as long as you say that every cas line goes this way and the other cas line goes that way, you can have multiple parallel paths, it doesn't matter. So we can solve that now and have a truly unordered fabric in the CXL. And of course, you got the fabric manager that's going to manage the resources. So fourth problem had to deal with effectively distributed computing, the fourth challenge. And that is, how do you build a truly composable system in a large scale, and how do you deal with it in a way where they can do load store based kind of message passing, which is very low latency, so that you can solve some of the next generation problems in an efficient manner. Part of it also has to do with, for example, you want, for example, a memory device to be able to do some amount of near memory processing, because it's inefficient to pull all the data, right? Simple processing, if you can do near the memory, that's great, right? The problem with the near memory processing is that the data is not coherent. So if you process it, that means you pretty much have to today flush all the data and make sure nobody else has it, change in your page table so that it cannot be cached by somebody. Then you can do the near memory processing. Now with back invalidate, I don't care. I can do near memory processing. If I run into a conflict, I'm just going to issue a back invalidate and I can get it done. So these kind of distributed processing and distributed resource sharing and pooling, of course, is what the fourth problem statement is, and that's basically what we have solved with CXL 3.0. So in conclusion, of course, full fabric capability and fabric management came with 3.0. We have expanded switching topologies from a single level switch to multi-level switches, of course, multiple parallel path. We look close to the symmetric coherency capability without being symmetric. Just the back invalidate just brings the essence. Peer-to-peer, we have the resource sharing capability without going through the CPU. We doubled the bandwidth with zero latency adder compared to the prior generation, and of course, full backward compatibility, right? And then the new usage models are memory sharing between hosts and peer devices, and between hosts by themselves, support for multi-headed devices, and global fabric attached memory for coherent global shared memory across hardware coherent. You can also do software coherent. And then, take a look into 3.0 spec, and we, of course, as I said, innovation doesn't stop with with third generation of the spec. It continues, and stay tuned for more things to come. So with that, questions? We got a few minutes, so. Okay. All right. Thank you all very much.